So this is the second video on the improvements to numerical methods for solving first-order ODEs, and in particular, I'll cover the Runge-Kutta method, both the second and fourth-order Runge-Kutta method. Runge-Kutta is so simple to code and use; it has become extremely or very widely used, and it's in fact probably the method you would use in the future to solve this sort of problem. In addition to being able to apply the Runge-Kutta method numerically, I'd also like you to be able to keep in mind how the accuracy depends on step size for second, again for the second and fourth order, for this second and fourth order method. So let's, before getting right into Runge-Kutta method, um, let's remind ourselves what the midpoint rule was like. So the midpoint rule used 2 points that were separated by 2 increments apart, right? So it started at yn minus 1 and estimated what y 2 step increments apart were based on the slope at the point in between those 2 points. Remember, f of x sub n yn is the slope between, or I should say at the midpoint, of xn plus 1 and xn minus 1. Now recall that the main disadvantage of the midpoint rule was that it is not self-starting. In other words, if we start off, we always start off with our initial condition, in which case n would be 2, and therefore we would know that y1 is our starting condition. But to evaluate the point at point 3, we need to know what the y value is at point 2. And so we can't get it started until we estimate y sub n was. And we talked about using a first order method, for example, at higher step sizes, to find x sub n in order for us to evaluate that first slope. And once we find that point at x equals 2, then we can apply the method and for the remaining points. So that was the main disadvantage. But Runge-Kutta gets around that. So, and the way it does it is, instead of estimating the midpoint between 2 points separated by 2 increments, we can estimate the midpoint between 2 adjacent points. So y sub n plus 1 is equal to, the first guess is y at the previous point, and we estimate the slope between those 2 points by taking the average of the slope at the first point, y sub the slope at xn yn, and the slope at the adjacent point. So in other words, the slope between, or I should say the slope at the midpoint, is estimated as the average of the slopes at the 2 adjacent points. Okay, so that seems logical. But the problem is, you'll see that y sub n plus 1 appears on both sides of the equation. So we don't know that yet. So we can't apply the method as it's written exactly like this, but we can approximate the position of yn plus 1 by using the slope at the first point. So we're going to approximate y sub x sub n plus 1 as y sub n plus the slope at the first point times h. And so the Runge-Kutta method, therefore, for second order is based on this approximation. Again, estimating the slope at the midpoint as the slope at the first point plus the slope evaluated at xn plus 1 and our estimate for the next point of y. So this is our estimate for the next point of y. So let me attempt to sketch this out so we can sort of visualize what we're doing here. We have point xn and we have point xn plus 1, and again the increment is h, the step size is h, and we're at our point x and yn right here. And we know what our slope is at that point. The slope is f at xn, yn. And again, the idea was to estimate the slope at the midpoint as the mean of this slope and the slope at the endpoint, but we don't know the endpoint, so we're going to estimate where the endpoint is by projecting along this slope to x sub n plus 1. So this is our estimate for our endpoint, and this is our estimate for xn plus 1 and yn plus 1. We know xn plus 1 exactly because it's defined by our grid, our increments, but we need to estimate yn plus 1, and that again was xn plus 1 times and then yn plus the slope at the starting point times our increment size. So that's that location. And then from there we can evaluate the slope at that point, and I'll sketch it like this, for example. And the slope is f evaluated at this location. And then we're going to take the mean of the slope at the starting point and the slope at our estimated endpoint, and then project along that trajectory. So let's see. So if our slope at our endpoint is, sort of looks something like this, it's almost horizontal the way I've sketched it. And then the mean of that will look like, we'll project along a trajectory, say that looks like this, and we'll get our next best estimate for y sub n. Sorry, y sub n plus 1. Okay, so that's the main idea, and of course we'll do that for subsequent steps as we proceed along. And so we could write this out very simply as y sub n plus 1 is equal to y sub n plus the average of two slopes, so that's why we're multiplying by half, and we'll write that as k1 plus k2, where k1 is equal to the slope at our start point times our step size, and k2 is equal to the slope at point x n plus 1, comma, yn plus k1. And that's all multiplied by h. So I'm just writing this out like you would write it in a computer code, but it's just another way of breaking these two parts into k1 and k2. Oh, and now that I'm looking at the equation, I'm realizing I forgot to multiply this average slope by h. This is an important correction that we should have, right? Because this was the estimate was for the new position is the starting position plus the mean slope times h. So we have to multiply by h, and this is the mean slope. Okay, that is an important correction. Okay, so this is how we would write out the second order Runge-Kutta method. So let's look at an example here. Better go to the next page to make sure I have enough room. So here we have our example, and the example is, say we're given y prime. This was taken from Greenberg's example for Euler's method that we looked at in the previous video. So again, we're given a differential equation of this general form in which the first derivative of y is equal to some function, and that's, in this example, that function is y plus 2x minus x squared. So, and say we're given the initial condition that y at point 0 is equal to 1. So the way we would write MATLAB type code would be, first we have to define the step size. So we'll say h is equal to, say, 0.1, and we put our semicolon as a common practice at the end of each line, so that when we run it, we don't see this displayed to the screen. And we would define our grid of x as going from, say, 0.0 in increments of h to some maximum value, and I'll just say 10, for example. And I like to make this a column vector by putting an apostrophe there, and again the semicolon. And then we need to define the maximum, total number of increments. I'll just call that n max, and that we can just say is the length of x. That tells, this is the number of points in our grid point. So this tells us how many points we're going to be estimating the value for. And so we could write a for loop a for loop automatically increments n from 1 to n max in increments of 1, right? And then k1 was equal to the slope at the first point, which in this case would be y sub n, or y at, or the nth number in a new vector y. Oh, actually I forgot to initialize our vector y. So let's say that y is equal to zeros size x. So this makes a vector with all zeros having the same shape or size as x. And then we also have to initialize the first point. So y1 is equal to 1. So this is the first value of y, which corresponds to x is equal to 0. Okay, so the initial condition was x equals 0, which is the first value in our vector of y in our MATLAB code here. Okay, so now back to our stepping through each point. When the first time through the loop, n will be equal to 1. So it will take y1, which we've defined to be 1, and then add and then calculate the slope based on that point. And the slope is given by this equation. So we say y plus 2 dot asterisk for a multiplication, x at point n minus x at point n dot, and then the caret, or the upward caret, 2, and that's the x, that's a way of writing x squared. So that's k1. Oh, sorry, we have to also multiply by h, and then k2 was the value of the slope at the estimated endpoint. So that is y sub n plus two star x n plus 1 minus x at the second point, n plus 1 squared, plus 1/2 k1. And I have to multiply that by h as well. So that's k2. And so for our estimate for our second point is, again, yn plus our estimate for the mean of those two slopes, or the estimate for our midpoint, written like this. Okay, so that is an example MATLAB code that you would use to solve this equation over the interval from 0 to 10. And oh, I'm also forgetting, I should subtract 1 here, because we want to, n is going to go from, say, 1 to the max, well, n max minus 1, because we're going to, when n is equal to n max minus 1, we'll evaluate the point at n max, the very last point. So we need this n minus 1 there, or else we'll get an error. So this is Runge-Kutta, abbreviated as RK2. So this is second order. And we would verify that the method is second order by taking the equation for this Runge-Kutta method right here and comparing it to a Taylor series expansion. And you can see, I encourage you to see pages 302 to 303 in Greenberg to see how he directly compares this equation to the Taylor series and shows that the truncation error, or sorry, the incremental, the local truncation error is of order h cubed, giving a accumulated truncation error of order h squared. And again, that means that the error is second order in h, and that describes the accuracy of RK2. Oh, and I'm catching one more mistake. This shouldn't be a half a K1, it should just be a K1, right? Because the second term was the slope evaluated at point xn plus 1 and yn estimated as the second point estimated as the sum of yn plus just k1. And so I just have a plus k1 right there. Okay. Oh, and just a couple little details here. We want the we're writing a MATLAB code on the as a lecture, so this is the n plus 1 point of x, and this is y. It's the nth point of y. So now let's talk about Runge-Kutta 4, RK4. So this is the fourth order method that has fourth order accuracy. And I'm not going to go through the derivation, but the equation that you apply is relatively simple. So again, we're estimating y at the next point ahead of y sub n. And here, instead of taking the weighted average of 2 points, or 2 values of slope, we're going to take the weighted average of 3 points, or sorry, 4 points. So we'll have K1, K2, a third of K3, and then 1/6 K4. So this is a weighted average of 4 guesses or estimates of the slope, and that's all multiplied by h. So the second order method was a weighted average of 2 guesses of the slope times h. This is a fourth order method, so we're going to have 4 terms here. And the 4 terms are k1 is equal to f, the slope at the starting point, just as in the RK2 times h. K2 is equal to f at x n plus a half a step ahead, so that's h over 2, and y at point n plus 1/2 of k1. So this describes where we're evaluating the slope. That's for the second term. For the third term, we have f evaluated at, and the second term is also multiplied by h. The third term is evaluated at point xn plus h over 2 again, but then at point yn plus 1/2 times k2 K2. This is K3, not K2, times H. And then the fourth term is K4 is equal to the slope evaluated at the endpoint, the second, well, the adjacent point, which is the endpoint in this step. And this is yn, y at point n, plus K3 times H. And so this is in a nutshell our K4, which has an incremental truncation error of order H5 and a cumulated truncation error of H4. So this has fourth order accuracy, which has a very high level of accuracy. And in your problem set, you'll get to apply this method to compare it to the lower order methods that we've discussed and see how it performs. So this concludes this video on Runge-Kutta method. Again, it's a very widely used method. It's simple to code and it's very powerful.